Hi everyone, I'm glad to present my work named Lead Instrument Detection from Multitrack Music here at ICASSP25. I'm Longshen Ou, currently in my fourth year of PhD program in the National University of Singapore. I'm currently working in the Sound and Music Computing Lab led by Professor Ye Wang, and this work was previously done during my internship at Yamaha Corporation, mentored by Yu Takashi-san. Okay, let's move on. Firstly, let me introduce the background and motivation of this work. The very first question will be, what is the lead instrument? In a simpler term, it just means which instrument is doing the solo part. For example, in pop or rock music, you might hear something like this. That is a very iconic guitar solo. When it goes off, our attention is immediately drawn to the guitar instrument. And in funk, there are like bass solo. In jazz, there are saxophone solos. And sometimes drum solo. And also the keyboard solo. But the most common type of solo is the so-called vocal solo, or just the human singing voice. On the dark desert highway, cool wind in my hair. So the term of solo means it attracts most of our attention, but not mean it is the only instrument being played. They are still played with other type of instrument, but they are the most obvious in this type of ensemble. There are several potential application scenarios if we can achieve automatic detection of lead instruments. Firstly, it can help us create better music thumbnail by including the most iconic instrumental solo part inside. Secondly, it may help us to achieve better music recommendation by also considering the lead instrument related information. Last but not least, it may facilitate the automatic mixing procedures by making it more explainable. Unfortunately, we did not find existing works that explore the same topic as ours. It seems that the content analysis for multitrack music is a very underexplored task where we haven't seen any existing works that is related to designing neural network structures in such scenarios. And there is also no open source annotated dataset in such scenario. There are some works regarding dealing with single mixer track or single instrumental track as input. However, they also have somewhat issues. For example, the flexibility issue. They always have some assumptions about the input audio should always be a combination of a certain fixed group of instruments. And there might be generalization issue where they cannot deal with new instrument they have not seen during the training process. And the performance is also not good enough. We have reproduced one of the previous guitar solo detection model, but the best performance it can achieve is just like 5% accuracy in our dataset, which is not very meaningful for real-world applications. Next, let me introduce more about the problem setting. This is the highest level diagram of this problem. We have a multitrack audio recording as the input. This is a group of audio, each of which belongs to a specific instrument in the band. And our goal is to determine which instrument is doing the solo part. There might be two different forms for the output formats. The first one is segment level classification, where our model output a single label for each music segment, indicating the most important lead instruments. And the second scenario is the frame level classification, where we want to determine the lead instrument at any given time step during this music segment. The second scenario is the focus of this paper, but we also conducted some experiments on the first scenario. Since there is an open source dataset on this problem, we have to create our own datasets as the very initial step to solve the problem. So here's what we have done. We have chosen two sources of dataset. The first one is the MJN events dataset, which is a series of live events inside the Yamaha Corporation. And to facilitate reproducing of our results, we also conducted annotation on the existing open source dataset called MedleyDB. So the annotation process is conducted within the Adobe Audition software, where we mark out the onset, offset, and the type of lead instruments throughout the entire songs or performance. Here is the statistics of the resulting datasets. We find that the MGN is a little bit larger, but the MedleyDB has a more diverse instrument settings. Here we show the label distribution on the two datasets, and we find that on both of the datasets, they follow a long tail distribution, where the vocal is the most common lead instrument, followed by the electric guitar. Then we checked the switching frequency of lead instrument, and the MGN dataset has a little bit higher switching frequency compared to the MedleyDB dataset. Next, let me introduce how did we solve the problem. There are two important components in the system. The first one is an audio encoder to convert the waveform of all the tracks to the corresponding feature map. And then those feature maps are sent into a classifier to obtain the final classification results. We adopt a self-supervised pre-trained model called MERT as the autoencoder module. It is very good at pitch and timbre related problem and very suitable for our scenario. The encoder's parameter is shared among all tracks, which means a single MERT will handle all the instrumental tracks. We offer several versions of classifier design, and here is the most simple version, where a linear classifier operates directly on the feature map of the mixer track without utilizing other instrument-specific tracks. In the second version, we want to use instrument-specific tracks to aid the detection, hence we average all the feature map together and then send the average feature map to the linear classifier. The third version of classifier design is the most effective one, which is called track-wise attention. We calculate a dot product attention across those feature maps, where the feature map from mixer track serve as query and other tracks serve as keys and values, so that it can handle arbitrary combination of instrumental tracks. This process mimics the human auditory attention, where when dealing with each specific instrumental track, we compare it with its context, in another word, the mixer track, to determine its importance and aggregates the feature accordingly. We have also tested two classification schemes. The first one is the instrument classification. We want the model to output the name of lead instrument directly. The second one is the track classification, where we want the model to locate the track ID of the lead instrument. So let's see how this method performs. Here is the experiment setting. Most experiments are done with the MJN dataset since we have better control over the instrument combinations. Specifically, on the validation set is a hard setting where we have different challenging cases, and on test set is a more balanced setting. As for the metrics, we adopted both accuracy and macro F1 as the metric. Since our dataset is highly unbalanced distributed, the F1 score is a better indicator of the overall performance. This table shows the main result. So firstly, the most simple model, which only takes in the mixer track, already achieved a decent score where it achieves like 57% of instrument F1 on the test sets. Both the track average and track-wise attention model can use the track-wise information to aid the detection, but the second type is much more effective, shown by higher instrument F1 and accuracy scores. If we switch the classification scheme from instrument classification to track ID classification, we can see the performance is further enhanced, especially in difficult cases, shown by higher validation set performance. We have purposefully included some samples with a new lead instrument, organ, in the validation set. This organ does not show in the training set at all, so that we can test the model's generalization ability to new instruments. We can see that with the instrument classification scheme, the accuracy on organ is 0, but we switch to the track classification, it achieves like 62% accuracy. This is not perfect, but already much better than the instrument classification. We also compare our method with some existing method like CRNN. This model structure is a widely adopted structure in sound event detection and a lot of audio-related tasks. However, in our case, we can see that the CRNN cannot perform meaningfully in both validation and testing performance. And no matter the input feature is MEL spectrogram or MERT features, and no matter whether the MERT model is fine-tuned together with the CRNN. We have also slightly modified our from mixture model to handle the segment level classification task to compare with the SVM model on the guitar solo detection. And it shows that our model has much stronger performance compared to the SVM model. Finally, I have put all the takeaways of this presentation to the next slide. We have proposed a new task, lead instrument detection from multitrack music, and crafted 2 datasets for this purpose, MJN and MedleyDB. We released the annotation for the second dataset for future use. And we have proposed a method containing a shared audio encoder and a classifier to handle this task. Specifically, we have tested the effectiveness of several classifier designs and 2 classification schemes. And also, in the paper, you can see that we have tested some additional components to aid the performance. We have established a strong baseline on both from mixture setting and multitrack input settings, and significantly outperform the existing SVM and CRNN models. And also, this is the first neural network design for handling the multitrack music analysis tasks, and we hope that we can offer some insights for future research in related tasks. This is the end of the presentation. Thank you all for your time and attention. If you're really interested in this work, you can scan the QR code for our paper, code, model, or dataset. And also, if you are a PhD student looking for an internship opportunity, I would really personally recommend you to have a check of the Yamaha's internship program. They will offer nice environments, supportive mentor, and probably you're going to have a fulfilling and fruitful experience there. Thank you.